Thanks for the introduction. Hello all, I'm Kostas Perles, and I'll present our work titled Symbolic Reasoning for Automatic Signal Replacement. This is a joint work with Jacob van Keffen, Isil Dilik, and Yannis Maravakis. I'm sure you all know that writing correct and efficient concurrent programs is extremely challenging. Motivated by this, and also by the fact that recent empirical studies have shown that programmers tend to struggle to make thread signaling correct, the emphasis of this work is to make thread signaling way easier for today's programmers. For the purpose of this work, we're considering concurrent programming using monitors, which is a widely adopted synchronization paradigm. When it comes to signaling, monitors come into two flavors. On one end, we have what are called implicit signal monitors, which, as their name indicates, they don't require the programmer to signal any threads. And as a result, they tend to be easy to write, but they are inefficient in practice. On the other end, we have what are called explicit signal monitors, which they do require the programmer to manually signal threads. And as you can imagine, they can result in far more efficient implementations, but these implementations are now way harder to write. However, since today we want our programs to run really fast, programmers tend to use explicit signal monitors in most of the cases. So the goal of our technique is to provide an implicit signal implementation which is not only easy to write, but is also efficient in practice. Before moving on, let's see how monitors in both of these two categories look like in a Java-like language. Here we see a simple implicit signal monitor, which in general require a level language module. In here we have a Java class that ensures the following things. First, it ensures that first it provides a set of available operations for the threads to execute within the monitor. It ensures that we have mutual exclusion over the thread shared state, and also provides a mechanism for threads to block their execution until a Boolean predicate becomes true. In the implicit signal case, this is being achieved through a synchronization primitive called wait until predicate, wait until. As its name indicates, given a Boolean predicate, this statement will block a thread's execution until this Boolean predicate becomes true. Here, it's up to the system to identify cases where the Boolean predicate becomes true and wake up threads appropriately. I think we can all agree that writing this type of monitors seems to be relatively straightforward. Now, this exact same monitor implemented as an explicit signal monitor is going to look like this. Generally, the philosophy is same as before, except for the fact that the wait until statements have been replaced by a mechanism called condition variables. Threads can perform the following operation on condition variables. First, they can call wait in order to block their execution until a Boolean predicate becomes true. Next, they can call broadcast in order to wake up all threads that are blocked on this condition variable. And finally, they can call signal in order to wake up just a single thread waiting on this condition variable. There are like two pitfalls in this setup. First, we might start forgetting to signal some threads and therefore introduce deadlocks. And also, we might tend to start producing redundant signals to avoid the previous scenario, but in this case will be inefficient since most of these wake-ups are going to be spurious. So now it's easy to see that things start to become a little bit harder for the programmer. To be more concrete, programmers tend to be overwhelmed with decisions whenever they try to write an explicit signal monitor. First of all, they have to decide whether a signaling operation is indeed necessary for every operation within the monitor. And if such signaling operation is indeed necessary, they have to decide between a signal operation and a broadcast operation. And this second decision is quite tricky because, for example, if a programmer tends to use always broadcast, this will almost guarantee that the resulting implementation is going to be correct, but it's going to be probably inefficient because most of the wake-ups are going to be spurious. On the other end, whenever a programmer chooses to use a signal operation, this has the potential to result in an efficient implementation of the monitor. However, now it's very easy for the programmer to introduce a bug where a thread blocks indefinitely. And this brings us to our approach, which on a high level works as following. Given an implicit signal implementation as an input, our technique is going to generate a semantically equivalent and efficient explicit signal monitor as an output. This way, we provide the programmers with a higher level of abstraction without introducing any of the runtime overheads associated with these implicit signal monitors. In order to do so, we introduce a tool called Espresso, which is designed to automate this task. On a very high level, Espresso consists of two concrete steps. It's first going to infer what is called a monitor invariant over the input implicit signal monitor, and then it's going to pass both the monitor invariant and the monitor to our signal placement algorithm, which is going to infer all the places and the type of signaling operation necessary in order to produce the explicit signal monitor at the output. Before diving into details for each of these two steps, let me first introduce the running example and all the appropriate jargon I'm going to use for the rest of the talk. Here we see an implicit signal implementation of a classical readers-writers log. This monitor is intended to be used by two types of threads, namely readers and writers, in the following way. Each type of thread has to first call its corresponding ender method. Here we have either ender reader or ender writer, access some resource, and then call its corresponding exit method. In order to enforce the desired synchronization strategy, the monitor may block each thread's execution in one of these two ender methods, since both of them contain wait until statements. For the rest of the talk, I'm going to refer to predicates appearing in wait until statements as wait until predicates. I'm going to refer to code snippets that can be executed atomically without having to block as conditional critical regions, or CCRs. And finally, let me introduce the notion of what we call a monitor invariant, which, not surprisingly, is a logical predicate that we can prove that it's being preserved over every possible CCR of the monitor. Now that we have everything in place, let's focus our attention in our signal placement algorithm. First I'm gonna talk about our signal placement algorithm, given that we have a monitor invariant provided by an oracle, and I'm going to defer the monitor invariant discussion for later. So the key idea for our signal placement algorithm is that it's going to reduce every possible decision with respect to signaling to appropriate Hoare triples. More specifically, given a CCR and wait until predicate, first, our signal placement algorithm will try to decide whether a signaling operation is indeed necessary. One possible outcome here is what we call a must not signal case, which means that there is no need to signal a thread after executing the corresponding CCR. If this is the case, then we are done. Otherwise, our algorithm is going to determine that we have either a must signal case, which means that we should always perform a signaling operation after executing the CCR, or a may signal case, which means that we should conditionally perform a signaling operation after the CCR. In both these two cases, we have to make another decision and pick either a signal operation or a broadcast operation. Now, let's further zoom in our signal placement algorithm and see how it can determine a must not signal case. For now, I'm going to assume that our monitor invariant oracle provided us with the invariant that the field readers of the monitor is always greater or equal to 0, which is quite trivial to prove over the implementation of the monitor. Now consider the following question. Do we have to wake up a writer that is blocked on its wait until statement after a reader executes its ender reader method? Here, the answer is no. And in order for our algorithm to determine the same thing, it's going to refine it to the following question. And also, please note that for the rest of the talk, I'm going to refer to the wait until predicates for writer as PW. So now, our algorithm is going to ask the following question. if we do have some writer threads blocked on PW, can we always prove that PW will always be false after executing end the reader? Now, in order to answer this question, our algorithm is going to turn this following question into a Hoare triple over the body of end the reader. Here, as our precondition, we're going to have that not PW holds, since this corresponds to the first part of the question, and it's equivalent of saying that there are some writer threads blocked on PW. And also our postcondition is going to be not PW, since we want to prove that PW doesn't hold after executing end the reader. Before moving any further, we're going to do the smart thing and strengthen our precondition with our monitor invariant. And now we're ready to throw this Hoare triple to our favorite SMT solver and see that it is valid. Therefore, our algorithm can determine that there is no need to signal any thread after executing end the reader. Another important thing here is to notice we cannot prove this specific Hoare triple without our monitor invariant, which really showcases the importance of automatically inferring such predicates. For the sake of time, I'm going to skip how our algorithm determines a main and a mass signal case. But the only thing you need to know here is like it's going to affect the generated code from our tool. Specifically, if we infer a mass signal case, we can perform the signaling operation unconditionally, and this is going to guarantee that we're not going to introduce any spurious wake-ups during runtime. And on the other end, our algorithm is going to fall through to a main signal case if it cannot prove something definite about a wait until predicate. And in this case, we're going to introduce a runtime check and perform the signaling operation only when the associated predicate with a condition variable holds. And we do that, of course, to avoid spurious wake-ups during runtime. Now let's go back to our bigger picture and see, and move to our second box here and see how our algorithm is going to decide between a signal and a broadcast operation. For that, let's again consider some blocked threads, some writer threads blocked on their wait until predicate PW. In order to decide between these two operations, our algorithm is going to ask the following question. Whenever we have to wake up a writer thread, do we have to wake up a single thread or multiple threads? In order to answer this question, our algorithm is going to analyze the last statement of end the writer method, since this is the statement that is being executed after a writer thread wakes up from its wait until statement. Specifically, our algorithm is going to try to infer how this statement affects the value of PW. Here, it's very easy to see that by executing writer in equals to true, this is going to make PW to false. So this is equivalent of saying that the first thread to execute after a signaling operation is going to falsify the predicate immediately, making it futile to wake up any other writer thread waiting on the same wait until statement. Therefore, our algorithm is now can safely infer that whenever we have to signal a writer thread, just the signal operation is sufficient. If such condition doesn't hold, our algorithm is going to conservatively choose to use a broadcast operation. And with that, I'm going to conclude my very brief introduction to our signal placement algorithm and move a step back and see how we can automatically infer monitor invariants. As we saw earlier, our signal placement algorithm is going to generate a bunch of different Hoare triples for every CCR, depending on the wait until predicate that examines at the time. The key point here is that our monitor invariant generator is going to try to maximize the number of Hoare triples that we're able to prove, since, as you can imagine, the more valid triples that we have, the more efficient the resulting monitor is going to be. In order to do so, we're going to take a demand-driven approach. And the key idea here is to combine abductive reasoning with predicate abstraction. On a very high level, first we're going to collect all the Hoare triples that our signal placement algorithm is going to generate. and then call a method named abduce on each of them and store the results into a set phi. You can think of abduce that works on the following way on a very high level. Given an invalid Hoare triple, it's going to return to us a precondition that it's sufficient to turn this Hoare triple from invalid to valid. So in that sense, you can think of our set phi here as a set of candidate invariants for our monitor. Now, in order to get the strongest possible predicate over phi, we're going to evoke a standard predicate abstraction algorithm, obtaining this way our final monitor invariant. And with that, I'm going to conclude the technical part of our talk. And let's move on and see how Expresso works in practice. In terms of implementation, we implemented Expresso as a program transformation using the STUD infrastructure and used Z3 to discharge any potential Hoare triples. We evaluated the effectiveness of the code generated by Expresso on several highly optimized and efficient monitor implementations, where most of them are drawn from very popular real-world applications like the Spring Framework and Gradle. We compare the code generated by Expresso with AutoSync, which is a state-of-the-art runtime system for implementing implicit signal monitors, which was recently published into PLDI as well. And we also compare the same code with the original version of the explicit signal monitor as taken from the application. Here we can see the results for a single monitor taken from the Spring Framework. And as you can see here on the x-axis, we have the number of threads currently executing inside the monitor. And on the y-axis, we have the number of, we have the milliseconds for each monitor operation. I'm sure here you can see that you can distinguish only two curves, which is good for our case because our curve overlaps with the explicit signal monitor implementation as taken from the project. And also AutoSync tends to add runtime overhead as the number of threads increases. And we can see that this same pattern holds for all the rest of the monitors that we have in our evaluation. So the main takeaway here is that Expresso is able to generate code that is almost identical to handwritten code written by expert programmers, and that it's also, on average, 1.6 times faster than AutoSync. To conclude, today I presented Expresso, a tool which provides an efficient implementation for implicit signal monitors. And more specifically, Expresso, given an implicit signal monitor as an input, is going to generate a semantically equivalent and efficient implementation of an explicit signal monitor as an output. We saw a case that Expresso is able to generate code which is almost identical to optimized handwritten code written by developers. And with that, I'm happy to take any questions.
Hi, thanks for the talk. So if you have a technique for generating correct explicit signal code. Do you also, are you kind of close to having a tool then that along similar lines can verify whether a given piece of explicit signal code is correct?
Well, I think like definitely this type of reasoning can be extended to verify, but I mean, there are like several technical complications, I guess, that one has to take into consideration, like the thread modeling and stuff like that. So as we saw earlier, as in earlier talks, our programs are like what are called like parametric programs. So you can have like an arbitrary number of threads executing. So this type of reasoning can be useful, but I don't know if it's like, it's going to be straightforward to, apply this type of reasoning and get something that like works for general problem.
I had one more question, was about your evaluation. So did I understand rightly that you started with explicit signal code and then you converted it into implicit signal,
exactly.
And then you saw whether your tool could get back to pretty good explicit signal code? So I guess I'm just wondering whether you could also evaluate on I don't know whether that's maybe like biasing towards code that kind of is particularly well suited for turning into explicit code, explicit signal code already. Whether you could also evaluate on code that's implicit signal to begin with, if you see what I mean.
Yeah, I mean, there are like not many cases where like people write things in the implicit signal setup, so it was like a matter of like getting the benchmarks, I guess, yeah. But the transformation is quite trivial, so you only have to remove all the signaling operations happening inside the explicit signal monitor, and then convert all the wait calls into the appropriate wait until statement. So, I mean, if you're already writing explicit signal monitors using condition variables, like it's kind of like suitable for like implicit signal as well.
Thank you.
Yeah.
I'm sorry, I have to answer his question for you. Historically, people started out with wait until expressions, starting with Dijkstra and moving on. And then turned them into icky explicit monitor code, but they started out with them in order to convince themselves that they were correct. So it's a little bit backwards in the assumption of that question.
If there's time, I'm going to ask this question. It might be a stupid question, but having a look at some of the example code you gave, it looks a little bit like the wait until tests, the test of whether a thread is ready to wake up, is in some sense running on the wrong thread. Could you have an alternative dynamic implementation in which one of these threads that's changed the state just runs everybody else's tests and figures out which of them should be woken up, if any?
So can you repeat, can you go closer to the microphone?
Yeah, sorry. Right. So it looks a little bit like in some of these cases, which maybe I'm misunderstanding, that you're worried about the cost of waking up a thread so that it can perform a test and go back to sleep. But it looks like that test is in some sense being run in the wrong place. Do you have enough information to copy the test that another task is going to run into this task so that we can just evaluate it here and decide whether it should be woken up at all?
Yeah, so like generally this is the techniques that like runtime systems like autosync do. So a thread at runtime tests whether, test a bunch of different predicates and test whether are some actually threads that have to wake up, and this thread is now responsible for waking up the rest of them. So, but as you can see from the valuation, this thing adds a runtime overhead.
Okay, fair enough.
Yeah.
Okay, let's thank the speaker again. Okay. So go ahead.